Hello everyone, welcome to my YouTube channel. Today we will learn about multi-stage op-amp circuits or cascaded op-amps. The topics covered in this video are cascaded or multi-stage op-amp circuits, voltage gain of multi-stage op-amp circuits with examples, bandwidth of cascaded op-amp circuits explained with examples, offset voltage of cascaded op-amps with examples, slew rate of cascaded op-amp circuits explained with examples. A cascade connection is a series connection of op-amps or a head-to-tail arrangement of op-amp circuits such that output of one op-amp is the input of the next op-amp. We can achieve both higher gain and higher bandwidth by cascading op-amps. But cascading will also increases noise and offset voltage at the output. So we have to trade off between both these advantages and disadvantages. Voltage gain of multi-stage op-amp circuits. When a number of op-amp stages are connected in series, the overall voltage gain is equal to the product of individual stage gains. This figure shows connection of three stages. The first stage is connected to provide non-inverting gain. The next two stages provides inverting gains. The overall voltage gain A of this circuit is given by A is equal to A1 into A2 into A3, where A1 is voltage gain of the first stage. It is non-inverting configuration. So voltage gain is 1 plus Rf by R1. Output is in phase with the input. A2 is voltage gain of the second stage. It is inverting configuration. So voltage gain is equal to minus Rf by R2. Output is 180 degrees out of phase with its input. A3 is voltage gain of third stage. It is inverting configuration. So voltage gain is minus Rf by R3. Again 180 degrees phase shift. This makes input and final output are in phase with each other. Since the overall voltage gain is positive, the circuit behaves as non-inverting amplifier. Let's observe this with an example. The figure shows multi-stage op-amp circuits. Find out peak output voltage for the given circuit. Here input voltage is 1 volt peak to peak. So the voltage gain of the first stage, it's a non-inverting configuration. So ACL is equal to 1 plus Rf by R1. 1 plus 10 kilo ohm divided by 10 kilo ohm, that is equal to 1 plus 1, that gives 2 as voltage gain of the first stage. Second stage is a inverting configuration. So ACL is equal to minus Rf by Rin, that is equal to minus 10 kilo ohm divided by 2 kilo ohm, that gives minus 5 as voltage gain of second stage. Third stage is also inverting configuration. So ACL is equal to minus Rf by Rin, that is equal to minus 10 kilo ohm divided by 10 kilo ohm, that gives minus 1 as voltage gain of third stage. Therefore, overall voltage gain of the given circuit A is product of individual stage gains. Gain of first stage A1 multiplied by gain of second stage A2 multiplied by gain of third stage A3, that is equal to 2 into minus 5 into minus 1. That gives plus 10 as voltage gain of this circuit. So output voltage V out is equal to overall gain A into V in. That is equal to plus 10 into input voltage 1 volt peak to peak. That gives plus 10 volt as output of this given circuit. Let's observe the output waveforms of each stage. First stage is non-inverting configuration. So both input and outputs are in phase with each other. Here gain is 2. So output voltage is doubled. Second stage is inverting configuration. So both input and output waveforms are 180 degrees out of phase with each other. Here gain is minus 5. So V out is 5 times of its input. Third stage is also inverting configuration. Here gain is minus 1. So output voltage is same as input with 180 degrees phase shift. Since our input and final output are in phase with each other, the circuit behaves as non-inverting amplifier. Find out the output voltage for the given circuit if V1 or input 1 is equal to 1 volt peak to peak and V2 or input 2 is 2 volt peak to peak. Here VCC or supply voltages for all these three stages are plus or minus 15 volt. First stage is inverting configuration. So ACL is equal to minus Rf by Rin. That is equal to minus 9 kilo ohm divided by 3 kilo ohm. That gives minus 3 as voltage gain of this first stage. So output voltage at point A VA is equal to ACL into V1. That is equal to minus 3 into 1 volt peak to peak. That gives minus 3 volt peak to peak output at point A. This minus sign indicates that both input and output are 180 degrees out of phase. Second stage is also inverting configuration. So ACL is equal to minus RF by Rin. That is equal to minus 12 kilo ohm divided by 6 kilo ohm. That gives minus 2 as voltage gain of this second stage. So output voltage at B, VB is equal to ACL into V2. Minus 2 into 2 volt peak to peak input, that is equal to minus 4 volt peak to peak output of second stage. This minus sign indicates that both input and output waveforms are 180 degrees out of phase with each other. This third stage circuit serves as summing amplifier of stage 1 and stage 2, and it is an inverting configuration. So Vout is equal to minus RF by Rin into VA plus minus RF by Rin into VB. Let's insert the values. Vout is equal to minus 10 kilo ohm divided by 2 kilo ohm into input voltage 3 volt peak to peak plus minus 10 kilo ohm divided by 5 kilo ohm into input voltage 4 volt peak to peak minus of 10 kilo ohm divided by 2 kilo ohm is equal to minus 5 into minus 3 minus of 10 kilo ohm divided by 5 kilo ohm, that gives minus 2 into minus 4, that is equal to 15 plus 8, that gives 23 volt peak to peak output of this circuit. Since the supply voltage is plus or minus 15 volts, so saturation occurs at plus or minus 13 volt. Here the output voltage 23 volt peak to peak far exceeds the saturation voltage level of plus or minus 13 volts. So the output voltage clip at saturation voltage of plus or minus 13 volts. The input signals and final output voltage is in phase with each other. So this circuit behaves as non-inverting amplifier. Now we will discuss the cascading of op-amps to achieve higher bandwidth. I have explained bandwidth in my earlier video of gain bandwidth product of op-amp. We take a quick recap of that. The bandwidth of an op-amp depends on its closed loop voltage gain. If you increase the gain of op-amp circuit, bandwidth will decrease. The gain bandwidth product of an op-amp denotes the relationship between its closed loop voltage gain and bandwidth. We can find gain bandwidth product in data sheets of op-amp. Gain bandwidth product is unity gain bandwidth. Let's assume gain bandwidth product as 1 MHz. So bandwidth is equal to gain bandwidth product divided by gain. Therefore bandwidth of the given circuit is equal to 1 MHz divided by 100, that gives 10 kHz as bandwidth of this circuit. So the bandwidth of this single stage op-amp circuit is 10 kHz with a gain of 100. Let's discuss how we can achieve both increased bandwidth and gain by cascading op-amps in series. Here we have two identical op-amp circuits and we have reduced our closed loop voltage gain of each stage to 10 to achieve a total gain of 10 into 10 is equal to 100. Here also assume gain bandwidth product is equal to 1 MHz as earlier. So bandwidth is equal to gain bandwidth product divided by gain. Each stage bandwidth is equal to 1 MHz divided by 10, that gives 100 kHz. Formula for total bandwidth is equal to bandwidth of each stage multiplied by square root of 2 to the power of 1 by n minus 1. Here n denotes number of stages. Therefore total bandwidth is equal to 100 multiplied by square root of 2 to the power of 1 by 2 minus 1. That gives 64.36 kHz of this dual stage op-amp circuit. So conclusion is that single stage op-amp with ACL is equal to 100, bandwidth becomes 10 kHz. If you use dual stage op-amp circuit with two identical op-amps with same gain, our overall ACL is equal to 100 and bandwidth increases to 64.36 kHz. Here we get increased bandwidth by 6.4 times. So from this example, we know that by using cascaded op-amp circuits, we can achieve both high gain and high bandwidth. Now we will discuss cascaded op-amp circuits offset voltage. Cascading of op-amp circuits increases bandwidth and gain, but also increases offset voltage at the output. The total output offset voltage is equal to the sum of the input offset voltages of each stage multiplied by the gain of every stage succeeding them. Here input offset voltage of the first stage is multiplied by the gain of the overall system. The input offset voltage of the second stage is only multiplied with the gain of second and third stage. The input offset voltage of the third op-amp is only multiplied by the gain of the third stage, so lessening the impact of the output offset voltage. This equation can be expanded for any number of gain stages. So the solution to overcome this offset voltage is, in first stage, use high precision op-amps with low input offset voltage and design a circuit with high gain at first stage will produce the best results. Let us observe this with an example. Let's take a high precision op-amp OPA2210 with a low input offset voltage of 5 microvolt and gain bandwidth product of 18 megahertz. Here non-inverting configuration. So ACL is equal to 1000. So our bandwidth becomes 18 kilohertz. Input offset voltage is 5 microvolt. Now dual stage op-amp with gain of 31.6 at each stage. Here bandwidth is increased to 364 kilohertz. Our input offset voltage is 5.17 microvolt. Now 3-stage op-amp circuits with gains of 10 at each stage. Our bandwidth further increased to 957 kilohertz and offset voltage is also increased to 5.19 microvolt. Let us observe this here. In this table, from single stage op-amp circuit to 3-stage op-amp circuit. Here the table shows how we have trade-off between number of gain stages with increased offset voltage and with increased bandwidth. For a low offset op-amp like OPA2210, the increase in offset voltage is minimum as compared to the increase in bandwidth. This highlights the importance of using high precision op-amp, especially in the earlier stages of an amplifier circuit. And one more important fact is that it is possible for op-amp with same wafer to have input offset voltage positive or negative polarity. This means it is possible for the offsets of various stages to either combine or cancel with each other. Now we will discuss slew rate of cascaded op-amp circuits. What is slew rate? I have explained this concept in my earlier video of slew rate of op-amp. Just take a quick recap of slew rate. Slew rate of an op-amp describes how fast output voltage changes in response to a change in its input voltage. It is measured as change of voltage in a given time, volts per microseconds. If we have applied a 5 volt square wave at the input of unity gain op-amp, our output must be same square wave of 5 volt. But output appears like this. This means output takes some time to reach 0 to 5 volt. The delay time to reach 0 to 5 volt is because of slew rate of op-amp. Slew rate of an op-amp is given in its data sheets. Now let's observe the slew rate of cascaded op-amp circuits with an example. Here 3 op-amps 741, 411 and 318 is cascaded in series. These 3 op-amps is configured as non-inverting amplifier. Their respective slew rates is also given here. We know that gain of non-inverting amplifier is equal to 1 plus Rf by Rin. The total slew rate can be set by any stage, as it depends on the gains of the stages. Perhaps the total slew rate is never more than the final stage slew rate of 70 volt per microsecond. To find the total circuit slew rate, let's start at the output of the first stage. First stage slew rate is 0.5 volt per microsecond. This is going into the next stage. Because second stage has a gain of 32, so it attempts to increase slew rate by 32 times. That is 16 volt per microsecond. But slew rate of the second stage op-amp LM411 is 15 volt per microsecond. Therefore, the 411 is the limiting factor at this point. So the slew rate is 15 volt per microsecond at the output of stage 2. This signal is applied to stage 3. Stage 3 has a gain of 3. So 318 triples its input slew rate, that is 15 into 3, 45 volt per microsecond. Because 318 slew rate is 70 volt per microsecond, so 45 volt per microsecond becomes the slew rate of this multi-stage op-amp circuit. This is how we can calculate multi-stage op-amp circuit slew rate. That's all about cascaded op-amp circuits. So if you have any doubts, do mention them in the comment section below. Thanks for watching this video. If you have learned from this video, please click the like button. Help others to learn by sharing this video. Please subscribe my YouTube channel and turn on notifications for more such videos. My next video is op-amp as summing amplifier. Have a nice day.